big welcome to another GraphGeeks Talk. This is where we explore the world of connected data. I'm your host today, Amy Hodler, and today you'll learn about graphs and LLMs, what can be achieved by combining them, and some of the current limitations. You'll also get a resources, a cheat sheet, and some code examples on Neo4j and LangChain. So we're very fortunate to have my friend Véronique Gendner. Véronique is a Neo4j ninja and a data processing expert. Over 25 years of experience with different aspects of information representations, database modeling, visual representations. Interesting side note about Véronique is that she became interested in graphs and the structure of graphs, which is a favorite topic of mine, while studying linguistics, and has done quite a bit of work using graphs and personal documentation, which is a kind of a fascinating area in and of itself. She's been exploring combining graphs and LLMs for better documentation access and investigations in general, like fraud investigations. So with a big thank you for everyone joining us, and in particular, Véronique, I'll turn it over to you and let you dive into the details.
Okay, well, thank you very much, Amy, for the opportunity to present this exploration of the graph and LLM world. Also, thank you for the feedback you gave me on the first version of the document that helped me complete it, the version I'm presenting today. So to make sure, right from the start, to make sure we understand each other, the left on this slide is what I would call charts. It's sometimes called graph, but when I'm saying graph, I mean what you see on the right. In an intuitive way, you can think of a graph as stuff related to other stuff. There's the mathematical graph theory, but you can also take it from an intuitive way and think of a graph of a formal representation that makes a relationship explicit. So let me first say a few words about how I got here today talking about graphs and LLMs. Languages is in the different aspects is the common thread in my different experiences: foreign language, linguistics, natural language processing, and of course formal language for computer programming. And as you mentioned, Amy, in the late 80s, 90s, and early 2000s, natural language processing was not just about LLM like it's today. We were working on linguistic formalism they were often tree-based, and tree are a specific kind of graph. So I consider that the first step of my journey into the world of graph. And then at the time, I also started doing data processing. In 2009, I started using the Brain, which is a personal documentation tool that allows to organize all your digital documents in a graph. So you have a graphical interface that allows to actually draw a relationship between notes, documents, any kind of digital element you may have on your computer, and you can visualize them on the screen. So this is how I started extensively using the graph structure with an intuitive approach. And the mathematical theory came in later. As the time, I was also doing data processing and visualization for user interface in companies. And then for 5 years, I worked for a research team. They were building a database for epidemiologists, and my job was to create and adjust web applications to help them process different kinds of data. So I first heard of Neo4j and Graph database in a meetup in 2013, and rapidly became a huge fan of ciphers. And then in November 2020, the ChatGPT meteorite hit the Earth. First, I tried to convince myself that the LLM was just another Californian hype that would pass. And for a while, I remained focused on graph technologies. But in August last year, Neo4j released a version that included vector index and vector similarity search And GraphRag started to be all over the graph tech world. Some presentations seem to go too good to be true, but still there seemed to be something to it, especially for leveraging documentation, which is one of my subjects of interest. So I decided to look into it. And what I'm sharing today is some landmarks concept that should help you navigate the field. I've represented them visually, so anyone, even with no technical background, can get a general idea of what can be done. So we will be starting with an introduction to graph, to label property graph database, vector search, text generation with large language model, what is RAG and GraphRag, and then we'll see different kinds of implementation with Neo4j core technology and plugins, with Neo4j Python module, and then with LangChain, the LLM orchestration platform. We'll talk about limitations, get an overview of use cases that leverage Graph and LLMs, and before wrapping up and providing some resource for further exploration of the field. So label property graphs, well, if you just hear for the name, you have the basic element that is in a label property graph database. That is, you have nodes, and nodes can, do you see my mouse? Yeah.
Yes.
Okay, so yeah, you have nodes here, and nodes can have one or several labels, and you have relations. And properties can be on nodes and on relation. And that's the vocabulary of a label property graph database. Then Cypher is the query language for those databases. And I really like it because it's very visual. If you have nodes like this, well, the corresponding Cypher query is rounded brackets, and the relation is between square brackets. So it's really, you really can see the graph pattern that you are matching when you write Cypher. Now, vector search, it's also often called semantic search, and it's about finding element through vector similarity. You have an embedding that is a vector representation. It can be of an image, a text, a sound, or different kind of thing. But here we're talking about text embedding. So the embedding of the question, and you have a vector index. So for example, here you have a question. You embed the question with an LLM to produce the embedding of the question. And this goes to the vector index. And with that, you get a list of results with a score for each result that you can, of course, sort by decreasing number. So this is what vector similarity is, and you can usually you set a k, which is the number of results you want in the decreasing order of the score. And as I mentioned, since it's been a year now, that you can have these in a graph database. That is, if you have a text property here, you can either you can have embeddings in two ways. You can import them from an external file, or you can build the embeddings from a text property of a node. So you on some of the side you have some technical details that I will not get into. You can get back to it if you want to dive more in the technical aspect of things. So yeah, here is how you can add an embedding property on nodes that will correspond to a text property of the node. And after when you have embeddings, then you build a vector index of those embeddings. And with that, you can do vector similarity search, just like we've just seen. if, for example, here you have a node that represents an organization, you have a text with the description of the organization and the corresponding embedding, then you can search the index to find the chunk of this document. If a document is represented here by different chunks of text, well, you can find which chunk of this document is most similar to the embedding of the description of this organization, which means this chunk probably describes something about this organization. Another vector similarity search you can do is outside. Here it was only between nodes in the database, but of course you can also do such a search with an external text, which is a question here. And so similarly, you embed the question, you get an embedding, you search with the index, and that's how you get the chunk, the most similar chunk to the question. Now let's talk about LLMs and text generation with LLMs. We'll see baseline generation, retrieval augmented generation, often called RAG, and graph RAG. For baseline text generation, you first embed the question, just like we've seen before. Then you use the LLM again for the stochastic information it contains, meaning that the generated text is the most probable sequence given the embedding and the question. Sorry, I'll do that again. So you use the LM the second time for generation, and you produce the most probable sequence given the embedding of the question and the model. The important thing to realize is that LLM encode two things. Information contained in the data is being trained upon, but also the capacity to produce human-like sentences. And baseline generation will fail if the requested information is out of the scope of the training area. If you didn't train your data on anything political about France, you will never get the answer to the question who was elected president in France in 1981. And the second limit is what's called the cutoff date. That is, the first version of ChatGPT had been trained on data until 2021. So any question about anything about after 2021 would fail because it was after the cutoff date. So to face that issue, you can use context. You can add context to your question for text generation. If, for example, ask what are the names of my cousin, of course, it's not contained in the model. But if I say, given this context, my father's brother has a daughter named Julia, my mother's sister has a daughter named Claudia, and a son named Peter, what are the names of my cousin? Well, in that case, the model can provide the right answer. And this is what is used for retrieval augmented generation. Well, as the name says, it's retrieval augmented with information, and this information comes from any kind of database. So you can use a specific, a private and updated knowledge base to get some information related to the question and provide it to the LLM. And so what is called the prompt, like namely the generation prompt, one of the things that is a bit puzzling when you get into the field is that since it's field in elaboration. The terms are still not settled. So you have to adapt to the variation of the way people use the terms, and prompt is one of these. Sometimes prompt mean just what I've called here the system prompt. The system prompt is something that is instruction that you give to the LLM about what you expect to present, what you want. And really, this was the weirdest experience in my developer's life, because you have to, like, the youngest among you have to realize that my generation, we started numbering lines to get the thing to do things in the proper order. So it was very formal. I think I have a whole part of my brain that is set to be formal when I address a computer. And so the first time I adjusted a system prompt and said, and I could just like sort of talk to it in plain English and even in French, it was really a shock. It was really a weird experience to me. So the generation prompt is made of three parts. You have the question, you have the content that feeds it with complementary information, and this instruction that is very important for all the kind of use case we will be talking about. And so GraphRag is another of those terms that have a meaning that is not really settled. Some people use the term GraphRag for things that don't even have RAG in it. And I think that's maybe stretching the term a bit too much for the sake of hype. I use the term GraphRag for a specific kind of RAG that is based on an external database that is structured in a graph. And so with that, you combine two kinds of relation. You have the stochastic kind of relation with the similarity search, vector similarity search. And here in the graph database, you have deterministic relation to produce information in a deterministic way. Like, for example, like in this example, you will do the similarity search on the embedding and come with this node that will, and the embedding and the plot and the corresponding plot are associated with the title. So that's the way you can produce the title of a movie similar to Toy Story. And the whole point of GraphRag is not just to use property on the node returned by the vector similarity search. You can leverage the power of any graph pattern matching around the node. In this example, the node representing a movie is related to a node representing the series it's part of, and all other episodes are also related to this node series. So when an episode is returned by the vector similarity search, then you can get any related information. Well, you can get, in this example, you can get the plot of all the different episodes of the series and feed that to the generation prompt. It's from an article by Christopher Bergman, so you can have the detail in the article here. Do we want to stop?
I will ask one question, and that's just about chunking and why graphs may or may not be a good option for chunking.
I'll get back to that question in a moment, okay, because this is related to something that I find very interesting in GraphRag. It's the fact that you can give source of information. So we'll get back to that in a moment.
Okay.
This is implemented in Neo4j database engine with 2 plugins. And the second way you can do GraphRag with Neo4j is with the Python module. So this module just changed name. It used to be Neo4j Gen AI. I just figured yesterday when I was checking on something that they changed the name. So yeah, maybe you need some adjustment with the documentation. This implementation seems to be currently changing quite a bit, and the LangChain integration that we'll be talking about in a minute seems a bit more stable. But if you want something simple, just Python module, that's the place to go. So to do GraphRag with Python, you will need retrievers. Retrievers are modules designed to retrieve documents from a vector store. So they can use vector store only or be combined with other retrieval methods. So here's the way you define the retriever. You set the driver to access the database. You decide you specify the name of the vector index in the database. You name the embedder. In this case, it's OpenAI that's being used, and you can also specify the properties that you want the retriever to return. And so invoking a retriever is just with a search method. With a retriever, you can add some metadata filtering. In the previous example, the first result of a movie about the famous sinking of Titanic was the movie Titanic, but you can filter here with the country of production, for example, and in that case, well, all the US produced movies will be filtered out, and you will get the UK-based movies only. So that's filtering on specific properties of node related to of the node that is returned by the vector similarity search. Another kind of retriever you can use is by combining the result of a vector similarity search and a full text Lucene index. So you send the question both to the vector similarity and the full text index, and you take all results and you reorder them to produce the result. Yeah, just like you could do GraphRag with Neo4j and plugins, here is what you do GraphRag with Python. It's the same idea. Like you get complementary information and you send it to the generation prompt. So it's just about the technical details and an article that you can use if you want to get more into the details. And now LLM orchestration platform, we've seen that vector similarity search and GraphRag can be done, yeah, I've just said that, with Gen AI and APA plugins and with Python. Now, in the LLM world, you have what are called orchestration platforms that are meant for chaining several components with LLMs. So those components can be splitting text in chunk. To start answering the question, Amy's question, like if you have an embeddings of a whole document, it will not be as precise as the embedding of a chunk, and so if you will get more specific information if you have the document chunked and embedding chunk by chunk. So you can point to the very piece of the document that answers the question, rather than a big embedding that will sort of mix everything up for a large document. So other thing you can do with orchestration platform elements is deciding between different process pipeline according to the question. You can format the output, you can, and of course you have all different processing involving LLMs. So Neo4j is integrated with LangChain, Haystack, Llama Index, etc. And the example in this document will be in LangChain, and you have some reference for the AMA index at the end of the document. So I will go quickly on those 3 slides because they describe 3 ways to build a Neo4j-based vector store in LangChain. You can refer to the document later for the details, but basically you can build the vector store upon an existing vector index, as we've seen the way you build a vector index in a graph database. The second way is with the method from existing graph. This is based on a label. You will select a label that will filter on some nodes with a specific label and build in the vector index with on the listed properties here. And the third way you can build a vector store in LangChain is with the from document method. This is because LangChain has a class document that is meant for different kinds of processing with documents, that is chunking and another kind of NLP processing on documents. So if you have a document in such a class in LangChain, you can directly build a Neo4j-backed vector store with this method. And after you build the vector store, you can do vector similarity search, just like in the introduction. So I don't think there's much to see here. It's like, it's about you embed the question and you get to the chunk with the corresponding embedding in the database. But this is to get the code for doing so in LangChain. Now, retrieval query. This is an important point for Graph RAG, because this is how you can fine-tune the graph pattern matching around the node returned by the vector similarity search. So here, the vector similarity search returns this node here, and the purpose is to get the previous and the next chunk together with the result node. So the similarity search will return a node and score. They are a fixed name variable, and so you can write whatever cipher query you like around the node to grab as many nodes and relation you want. And from this pattern, from this graph pattern, you can select any properties you want and return them as metadata. So here, the result of this retrieval query will be that this source property will be provided together with the concatenation of the text of the tree chunk, and here is where you concatenate the text. So this is really where you get the graph structure, where you get the graph structure potential for Graph RAG. And it's pretty straightforward to turn a vector store into a retriever in LangChain. You just add as retriever method, and as a retriever, the vector store can be chained with other elements in LangChain. So, do we have question or?
Yes, there is a question. So it's a great pause point. So there was a question about, and this is from Avi. Can you build the vector store from graph on multiple nodes? So can you use multiple nodes to create your vector?
I don't think so. You can use several properties of one node. You can concatenate several properties of one node to build the embeddings, but I don't see how you could do that. To use several nodes as a single element in the index, I don't think you can do that. Okay. So this is another way to retrieve information from the graph database. It's about using the similarity vector store and a full text index again, but through an entity recognition that will help you, that will produce two kind of context, an unstructured context here, just like we've seen before with similarity search. And here around the node, we grab all relation related to Elizabeth. Here, Elizabeth first has been identified as an entity. And so we can grab that node and all the relation around that node and produce this as a context for the generation prompt. A totally different way of getting context information for the generation prompt is cipher generation. So in this case, there's no vector similarity search. You just turn the question into a cipher query with a prompt, a specific prompt to the LLM that instructs the LLM to produce a cipher. And so the cipher is simply run against the database to produce the context for the generation prompt. And here is one of my favorite features of the combination of graph and LLM, and it relates to this chunking you were asking about. Like, it's one of the limitations of LLM is that the response they generate is not explicable. You have no way to know where the produced sequence of words comes from. If you augment generation with a graph structure database, you can provide metadata about the piece of text that has been used, and that is the metadata about the source of the LLM, the source that the LLM actually reformulated. So, for example, in here, if we have the State of the Union, the document with the State of the Union, and we chunk it in smaller pieces, so every piece is more centered on one, on a smaller number of subjects, and we do this similarity search with the question, what did the president say about Justice Breyer? We'll get this chunk with a similarity search, and we can return the chunk ID together with the text of the chunk. And so when the response is generated, the source can be provided, and this gives the explainability feature to generation, because if what the LLM has generated seems not very trustful, then you can check the source that has been human written and on which the LLM has based the generation. Now, so far we've seen how LLMs and graph can be articulated for information retrieval. But LLMs are also used to build graph. It's then often called a knowledge graph. What the LLM really does is entity and relationship extraction. And then they can be knitted into a graph. Now, the term knowledge graph is currently often used in such a broad sense that it's sometimes not very different from simply graph. I prefer to preserve the term knowledge graph to a kind of graph in which entities and relations have been organized by a human. Automatic extraction, which is just calculation of entities and relations, can be useful to build such knowledge graph, but it does not produce a knowledge graph in that sense. It doesn't produce a knowledge graph by itself. It takes human adjustment to make sense of a graph and turn it into a knowledge graph. So you can try entity relation extraction in a no-code with the Neo4j LLM graph builder, but you have in that no-code implementation, you have no parameter adjustment possible. If you want to have a hand on the parameters, you can try the LangChain LLM graph transformer class. The allowed node and allowed relationship can restrict the list of nodes and relations that can be recognized. And this helps prevent the default behavior of LLM that tends to overgenerate, especially entities. When you just feed the LLM with a document, it will probably generate a lot of entities. And so if you restrict to allowed nodes and allowed relationship, you will only get person, location, and date in this case. I would not dare pretend this presentation of how graphs are used in articulation with LLM is exhaustive. It feels like another usage is popping out every other morning. So let me just mention this lead. I have not looked into it, but it looks promising. It's corrective RAG. The thing is, when you retrieve information to the generation prompt, if what you retrieved was garbage, well, garbage in, garbage out. So one option is to evaluate the relevance of what you've extracted before sending it to the generation prompt. And graph, this is posed by Tony Seal, who calls himself the knowledge graph guy, and he's describing how graph can represent, organize in a graph reasoning way the way that you can use or not use or add complementary process according to the relevance of the retrieval. Now, about limitation of this approach. LLM results are stochastic. This means different runs do not necessarily get you the same exact result. And this is a challenge when you want to improve the process and you don't know whether the different result you have is due to what you've changed or the variability of the stochastic result. And given this limitation, cipher generation often is inconsistent. There are attempts to correct generated queries with a database schema, but it only works if the user knows what in the database and how to ask. So I've not yet seen a real-life use case where cipher generation seems to make more sense than the parameterized queries. Because if I'm a developer, I prefer parameterized queries because I know what I'm getting. And if it's for no-code users, then if they need to know what's in the database, I mean, maybe I haven't looked into it sufficiently, but for now, it seems to need more work to be efficient. Entity, as I mentioned, entity relation extraction with LLM tend to overgenerate. It seems to be, for different use cases I've seen, it seems to be a useful tool, but people who tend to, present it as a click button way of generating knowledge graph, that's a bit of what I call snake oil, it's a bit oversold. So human work still is required to obtain a valuable knowledge graph. And last but not least, the limitation I want to mention is the cost. And this I've heard from different presentations of LLM, of people working on LLM with graphs. The first cost is financial. Commercial API have a per token price, hence a significant cost for large data sets. My next step is to look into the open source and the smaller model that you can train and use by yourself. But the problem might be then that the result might not be as good than with the big commercial API. Another cost that I want to mention is the environmental cost, because hardware and energy consumption for LLM training and usage, it's the training and the usage that have environmental impact. And I think we cannot dig our head in sand and just move on, head in the handlebar, because chasing the hype and the fun, because it's fun using LLMs, I think our responsibility of professionals in the field is to take environmental impact into account. The problem, of course, is what is to be done, and there's currently no clear-cut answer to that question. But one thing I think we definitely can do is educate ourselves on that aspect. And Sasha Luciani, who's at Hugging Face, she works on the environmental impact in AI at Hugging Face, and she recently published an article that really get some starting point on that question. Let me say a few words about use cases I've seen. I've packed them into two main domains: text generation for recommendation, like email generation, for example, for recommendation. If you put some product in your chart and didn't buy it, then they can send you an email and recommend other projects. And the second large domain I've seen LLM and Graph in use is for leveraging the content of all sorts of documentation. So if you're aware of a use case with Graph and LLMs that wouldn't fit in any of those two categories, please do share in the chat. And so leveraging the content of documentation is really what is exciting, because of the zillion of terabytes that are available, and the difficulty we have to get the right information at the time we need it. So in the aspect of leveraging content, you have entity and relation extraction. GraphAware did that on the Rockefeller Archive Center documentation. It's about funding of science, and by extracting entity and relation, they managed to find sort of central node in the world of science, that is a researcher who are influential for funding of science. And so, those who also are influential, even in areas that are not their specific domain. And then there are all sorts of use case to access specific documentation. Norm and regulation and legal documentation are very good candidates because they intrinsically have a formal, they're already a bit formally structured, so it's a good starting point to build a graph, because like typically in legal documentation, you have reference to another, a paragraph that reference to another paragraph. So this is a structure that can be used. You have a LinkedIn use case for customer support that uses relation between different issues to speed up the response. And any kind of enterprise knowledge really can be processed this way. Neo4j is as example with risk analysis documentation for the pharmaceutical industry, for quarterly report in investment banking, and etc. You have a use case in financial documentation, in biomedical documentation, in scientific literature, for press article. So really, I think this is where there's a very good potential for this LLM and graph technology. Now, before I wrap up, I just wanted to emphasize that building a graph is making a structure explicit, and vice versa. Making a structure explicit can be done by building a graph. So this is what graph can bring to LLM, and that's by definition of what structure is, because structure is the arrangement of relation between parts and elements. So yeah, this is where you have the piece of a graph. And so common formal structure are just specific kind of relation, like this, a specific form of relation that you can have in a graph. But in a graph, you can also have any form of pattern for node and relation. And so this can represent many different things. It can represent an ontology, the domain representation, a workflow, set of rules, the structure of a documentation, and really like the limit is your imagination and your analysis of your data. So LLM produce the most probable word given some statistic learned on a corpus and the embedding of generation prompt. Those statistical production have proven astonishingly good at taking the form of what we all recognize as human language. LLM have something that has the form of a linguistic competence, but they produce stochastic results. Graph, on the other hand, represent information explicitly in an accurate and deterministic way. They are a very good way to represent domain-specific and updated information to feed the LLM with. So in a way, with Graph, you can get the LLM to sort of focus on a specific information that have been extracted based on explicit relations. And the lack of explainability is another lowdown of LLMs. All the information is mixed together. When you get an answer, there's no way to figure out where it comes from. If you have part of the generation process based on deterministic relation represented in a graph, you can, for example, provide a piece of text that generated the answer. So the graph adds some interpretability to the process. Yeah, as you probably figured by now, I'm very excited by the documentation, information retrieval in documentation, and that's because with graph you have, with graph database combined with LLM, you have three possible kinds of search: the keywords and Lucene full text search that we're all familiar with, but also the symbolic graph pattern matching possibility to search for information by explicit and deterministic relations. And the third way to search information is the subsymbolic, the non-deterministic vector similarity relations. So all this makes the graph and LLM technology combined like a very promising field for information retrieval. Okay, so here are some more resources that you can explore to go further in different directions. Yeah, maybe we have a couple of minutes if you have questions.
Yeah, awesome. Thank you, Véronique. So much good information and links and things that I think I'm going to use this for a study guide, really, is where I'm going to start with. But we do have some questions. In your opinion, how effective are graphs and LLMs together when trying to work with semi-structured and unstructured data? So including things like tables and visualizations and things like that. So trying to mix all of that together.
Yeah, that's exactly. We've seen one of the example where you can use both. We all know what we're talking about when we say unstructured data that is plain text, and so yeah, you can have both in a graph database anchored LLM generation. You can use the chunk of text associated with the node, and that's just plain text. and you can use the relation between the graph pattern that are a formal kind of data.
So I think we have time for maybe one more question here. Do you know of any LLM based on graphs? So it'd be LLMs and graphs together for detecting crimes. So any kind of security, fraud, things like that. Do you know of any use cases in that scenario?
What is used in fraud detection is entity extraction and relation extraction, and more importantly, like entity resolution. Entity resolution is when you've extracted entities. Maybe you have two nodes representing the same entity because there's just a typo or there's some formal difference between the node. And so entity resolution is about merging them. And so, yeah, that's a common, that's something people working in the fraud, in the fraud detection industry work on.
Awesome. Well, I think we're going to have to leave it there for now. We're at time plus, but again, thank you. We will try to follow up with individuals who had questions. As Mia put in the chat, join the Discord server, join GraphGeeks.
Sorry, I did wanted to say that because GraphGeeks is a really great place, because it's vendor independent, so you can really have good conversation with people about graphs, and yeah, do come on GraphGeeks.
Come join and talk to us. All right, Veronique, thank you again for your expert review and for putting together this resource. I know it represents a lot of work. So thank you, everybody. We'll see you all online.
Okay, bye. Thank you.